Algebra 2 Skills number 44, natural log and e. Okay, so this is an introductory to a calculus concept. So let's look at what e is. E is going to be equal to this expression as n gets very large. There's some calculus notation that we could use here, but being an Algebra 2 slideshow, we're not going to do that. But as n gets bigger and bigger and bigger, then e approaches a particular number. And that number is irrational, 2.718, and it carries on from there. And this may seem like some random process and some random number, and you might wonder, well, why do we give this a particular name? I do want to express that e is a variable. It is not a variable here. It is a known value. So e is not a variable. It appears like one, but it is a known value of 2.718. So what is it particularly about this number that's so special? I want to do a Desmos demonstration to show you what we're looking at. There's an exponential graph that you may recognize and a second exponential graph, and what we want here are for these two graphs to meet, basically. So let's look at, I'm going to go off the slideshow here just to show you what I mean by this. So what we have here is this, again, this is Desmos. This is the graph of an exponential, and this green graph represents something called the derivative. Again, that's a calculus concept, but basically the derivative tells you at the rate of change for the red. But I have a slider over here, and this is the base of the exponential. So watch what happens when I get closer to that 2.718 number. Look at the convergence there. The red's moving, but so is the green. But you can notice the gap between them is closing. As I get close to 2.718, notice the gap here is very small, and this slider only goes to tenths here, but when I get very close, now you see a very small gap if you look closely. But as I get on 2.7, it appears to be the same graph. Okay, there's 2.7. If you zoom in, there's still a very small gap there. If you could get that to 2.718, which this slider, we're not going to get it to exactly 2.718. Just for time's sake, but there is a small gap there. If I could make this exactly 2.718 or very close to it, that would be even closer still. As you go past 2.7, notice that the gap begins to open back up. Okay, so that's the significance of e, is that basically the graph and its derivative is the same. The rate of change is the same as the function itself, which for now, that's not something we need to concern ourselves with so much, but it does help to get somewhat of an idea of why that's so special when it seems so random. Okay, so that's e. So the natural log is just simply the log that's associated with e. You're not going to see this very much. You'll see ln instead. I know it seems backwards just because it's from the Latin root, natural log, ln is what we say. So you're not going to see this, but it means log base e. So the natural log of e to the x would be asking e raised to what power is e to the x, and that, of course, would be x. So there's an understood e there. So it just gives you an idea. When you see ln, that is a log, but it's specific to log base e. E gets its own log. So look at a couple examples with this. So how about a natural log equation? Again, understanding this is a log, there's a log base e, so I change forms. We only have the one log here. We're going to change forms. E squared is 2x minus 1. Now e is that 2.718 number, which is only approximate. It does go past 2.718, but that is programmed in the calculator, so I can go e squared, and in the calculator, this is approximate. You're going to have to deal with decimals here, but now we can just finish that. Add 1 and divide by 2. Again, this is to the nearest thousandth. Okay, so that's not exactly the value, but it's very close. A second example, what about an equation, an exponential equation? Well, again, we want to isolate this exponent right here. So I want to add 5 to both sides, then divide by 3. Those are natural, no pun intended, natural steps there. Now, e raised to x plus 6 is equal to 9. What we want to do here is take the log of both sides. But for e, you could just put a log up there, and that would be fine, and just move the x plus 6 up front. But with e's, we have a special log called a natural log. So what we can do here is take the natural log of both sides, and instead of fooling with putting x plus 6 up front like we do with most exponential equations, the natural log and e, they just, in a sense, they cancel here. e raised to what power is e to the x plus 6 power? Well, that would just be, oh, same line here. That would just be x plus 6. So the natural log and e more or less cancel here. And then on the other side, of course, the calculator is programmed. It understands that e to the 2.197 power approximately is 9. And now you can just subtract 6. So just give you some idea of what e is, and the fact that natural log is the special log that goes with it. One more thing I'll say here, e is called the natural base. I didn't mention that earlier. And so natural base would go with a natural log. So that's e.